Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, in part 5, I'm going to talk about one of the most fundamental concepts in machine learning. We will see what do we mean by model bias and model variance, and basically how the combination of these two concepts is going to help us finding the optimal complexity of our machine learning model. Okay, now what is model bias and model variance in machine learning? Remember, when we talk about bias and variance, these are the properties of repeated sampling and not just one realization of the data, right? So we have to be careful that we are dealing with repeated sampling, okay? Now let's start with a very simple example. Imagine this is our target variable and this is our only one feature in the dataset. And the black line is the unobserved true relationship between the observation and the data, right? Our machine learning model is expected to estimate, to learn this pattern in the data. And imagine the pattern is just this simple curved line, right? The black curved line. The machine learning model is expected to learn this pattern, okay? Now, imagine the first model that we're going to use is a very simple linear regression model, and it's actually the most simple form. You know, we think of the, let's say, the average, right? So this is going to be our model, right? So this is our very basic model, this line. Now, I want you to think about what happens to this model, what happens to its variance, and on average, how it's capturing the pattern if we change the sample, right? If we work with another sample. Now, if I simply use another set of data set, let's say the red ones, right? And the model is the same, so the new fit is going to be, maybe this is going to be just a slightly different, right? Maybe this is going to be the new fit. And as you can see, on average, I'm talking about average of these lines. On average, the model is off. It's not capturing the true pattern. Remember, the black one is a true pattern. And on average, we are not capturing that. So this concept is what we call bias. So in this simple example, bias is going to be very high because on average, we are not capturing the pattern. Okay, but what can we talk about the variance? I want you to think about this blue line and red line. So these are only two realization of the data. What if you're repeating this process thousands of times? So the variance is going to be very small, right? Because as you can see, for every realization, the model is super simple. And for that reason, it's not capturing the let's say, the average pattern in the data. And the variance is going to be also very small, right? So in this example, we showed that if the model is very simple, the model bias is going to be high and model variance is going to be small. Okay. Now let's look at another example. Now let's focus on very complex model, right? So in the previous slide, look at the very simple example, simple machine learning model, and we saw that the bias is very high because on average it's not capturing the pattern and the variance was small. Now let's focus on a very complex model, and by complex model, for example, you can think of a polynomial regression model with very high degree of polynomial, right? It's super flexible. Basically, it's capturing unnecessary noises in the data as well, right? So let's exaggerate a little bit and say that this model is super complex. So if the model is complex, what is it doing? So it's going to do something like this, right? Maybe for this realization, the model is going to capture everything, right? It's going to perform a very good job in terms of fitting the data, right? And now let's look at another realization. So here is another realization of the data, and the model is going to do something like this because the model is super complex, right? Now I want you to focus on these two lines, right? The green one and the red ones. And remember, the model is super complex. So what can you tell about the variance of the model? As you can see, the variance of the model is going to be very high, right? Because if you look at the model fit for different realization of the data set, we see that the variance there is going to fluctuate a lot. Compare the green curve between and the red curve, right? So the model variance is going to be high. But what about the model bias? So what can we say about the model bias? Model bias. Remember, go back to the definition of model bias. On average, are we capturing the pattern in the data or not? On average. So it means that if I do thousands of auto realization, right? So maybe this is one, this is another one. Let me use another color. Maybe this blue one is another one. But as you can see, on average, it is capturing the true relationship between the data, which was that black f of x, right? So the model bias is going to be small, because it's on average, it's capturing the true relationship, that nonlinear curve in the relationship in the data, right? So in this example, we show that if the machine learning model is super complex, the model variance is going to be very large, but the model bias is going to be small. So as you can see, there is a trade-off between bias and variance, and this is what we mean by the bias variance trade-off in machine learning. And again, I repeat myself, remember, bias and variance are the concepts of the properties of repeated sampling, not just one realization of the data. Okay, now let's see how we can quantify the bias variance trade-off by looking at MSE decomposition. So we can show that, we can mathematically show that, and this is actually what I'm going to show you in the next slide, that mean squared error is going to consists of three parts: model variance, model bias, and irreducible part. Okay, so as we talked about it in last slide, model variance is the variance if we had estimated the model with a different training set, okay, or with a different data set, basically. Model bias is the error due to using an approximate model. If the model is too simple, we show that the model bias is going to be high. If on average we are capturing the pattern in the data or not. And the irreducible error part is basically due to some missing variables and some limited sampling, right? It cannot be fixed by modeling. So the goal is to minimize the sum of model variance and model bias. So the goal is to minimize the combination of the two, okay? Because remember, this part, the irreducible part, cannot be fixed with modeling. So if you want to make sure that the model variance and model bias are a combination of the two is the smallest, we have to, this concept is known as bias variance trade-off, because reducing one will lead to increasing the other one, right? We showed the visualization in the previous slides, right? When the model was super simple versus when the model was super complex. Okay. Choosing the flexibility of f hat of x, basically this is what the model is learning, the true pattern in the data, is going to lead to bias variance trade-off, right? So if your model is super simple, the bias is going to be high, variance is going to be small. If the model is super complex, the bias is going to be small and the variance is going to be large, right? So a best combination, of course, is going to be somewhere in between. Okay, now let's see if we can mathematically decompose this MSE, mean squared error. As we stated earlier, the bias variance trade-off is one of the core concepts in supervised learning, right? Assume that the data is generated by a very simple model, and this is our model. Our target variable is a function of x. It can be, we can add the parameters and hyperparameters as well, plus some noise. And this is a property of our noise, right? On average, there's 0, and the variance is constant. The estimated model will be something like this. Our y hat, these are the predicted values, is equal to f hat of x. So this is what the model is going to learn, right? And then we can decompose the mean squared error by writing this equation. So we are interested to see what is the expected value of epsilon hat squared. So this is our mean squared errors, right? And then by definition, it simply is as expected value of y minus y hat, or f hat of x to the power of 2. We can just, instead of y, we can replace the f of x plus epsilon. So this is our y, and then simply square it, okay? Then we can use the properties of expectation, and we already know that the expected value of epsilon is 0, so we can reduce this one into two parts, the irreducible part and total quadratic error. Okay. Then we can use some properties of conditional expectation and open up this squared version. And after doing some simplification, we get to this two equations, right? We will see that this equation on the left-hand side is a combination of variance of the model, variance of f hat of x, and bias squared, right? And remember, this expected value of f minus f hat is the definition of bias on average if the model is capturing the pattern or not, right? How off we are from the true pattern in the data, plus that some irreducible part. Okay, so this was the mathematical version of the NSC decomposition. All right, now let's visualize the bias variance trade-off. Okay, so imagine, we already showed these things in the earlier slides, but let's quickly review them and put them together, the model bias and model variance, and see what is the optimal complexity level. Okay, so on the left, we have a very simple model, and we know that if the model is simple like this, the bias is going to be high, because on average we are not capturing a true pattern in the data, but the variance is going to be small, because if I look at different realization of the data, that flat line is not going to change a lot, right? On the other hand, if the model is super complex, we know that the variance is going to be high, because if I look at another variation of the data, it's going to be a lot different than the first one. However, on average we are capturing the true relationship, right? So on average the bias is going to be smaller. So as you can guess, a best combination is going to be somewhere in between, right? A model which is not super simple, or the model which is not very flexible, right? Then mathematically, how we can get to that point, right? So the idea is that we can plot the test error versus model complexity, right? So on the left, the model is super simple. On the very far end, the model is complex. And we are interested in to look at the performance metrics in the test error, right? Because guys, remember, we have to look at the metrics. For example, this is regression analysis. We can look at the RMSE or MSE itself in the test set, because we want to test the performance of the model on a data set that the model has not already seen, right? We don't want to cheat here. We want to make sure that we're reporting these numbers for the test set, okay? So if the model is simple, we are on the left side, and we already showed that when the model is simple, the bias is very high, right? So let me use blue, so the bias is going to be very high. And the variance is going to be very small, right? If you're on the far right hand, when the model is super complex, the bias is going to be small, because on average we are capturing the pattern. Remember, on average we are capturing the pattern. However, the bias is going to be very large, right? So if we add these two together, this is our total test set error, which, let me actually use another color. So this is how it's going to look like, the combination of the two. Variance plus bias squared plus irreducible error. And as you can see, when the model is super simple, this is high, and when the model is complex, this is also high. So an optimal level of complexity is that, so if you start with a very simple model, we go to the right. If we start with a very complex model, we go to the left, and hopefully we will end up somewhere in between, right? Okay, so this is one representation of bias and variance trade-off, and there's another one which I'm going to show you on the next slide. Okay, here is another representation of the bias variance trade-off. So I can actually divide this quadrant like this. We have low bias versus high bias, and low variance versus high variance. Of course, ideal case, the best case scenario is going to be low bias and low variance right here. Look at that. On average, we are capturing the pattern, we're hitting at the target, and the variance is very small. Remember, this never happens. We cannot have the best of both work together, right? So this is ideal, which rarely happen. The worst case scenario is like this, that we have the bias is high, as you can see on average. So if I take the average of these black dots, maybe this here is the average. On average, we are off from this, maybe from the center of the from the center here. And on average, we are off. And the variance is also high. Look at that, black dots, right? Black circles. So this is very bad. This is a worst case. So ideally, we want to end up with, somewhere that's there's a combination between bias and variance, right? So here, on the lower left quadrant, the bias is high, but the variance is small. You can look at the black circles. So they're close to each other, so the variance is small, but the bias is high because on average, if I calculate the average, this is going to be the average. On average, we are off, right? And on the so what is this model? Do you remember? So this is going to be an example of a simple model or a complex model. Yes, a simple model, right? When the model is super simple, the bias is going to be high, but the variance is going to be small. On the other hand, if the model is complex, we are here. When the model is complex, the bias is going to be small. What does it mean? If I take the average of these black circles, maybe I ended up here, which is very close to the yellow circle. So on average, we're hitting at a target, but the problem is that the variance is high. So if you look at the black circles, the variance is high. Okay, so this is a complex example of complex model. And this is a representation of bias variance trade-off. And we hope that, I don't know, maybe we end up somewhere here in between. Wherever we get the minimum value for the our performance metrics in the test set. Okay, now let's talk about the concepts of overfitting in machine learning. Overfitting happens when the fit algorithm does not generalize well to new data. Basically, it means that if you use another realization of the data, the model is not going to do a good job. Let's look at a bunch of examples. So this is an example in regression analysis. So imagine we have our output variable on the y-axis. This is the output variable is going to be continuous, and on x-axis we have just one predictor, right? So the first model, and imagine this is the model that we're using, the dashed black line. And of course, the true relationship in the data is going to be something like this. Okay, so this black dashed line is going to be a very simple model. So if the model is simple, go back to the definition of bias variance trade-off, right? Model is simple, bias is going to be what? Yes, bias is going to be high and variance is going to be small. When the model is complex, bias is going to be small and variance is going to be high. And maybe this is a good combination. However, we are going to give this super complex model another name as well. So this is what we call overfitting. When the bias is small and variance is large, and this model is a very good example of overfitting model, right? Because it does not generalize well to another data set. If I use another data set, maybe by data set I mean another representation of the same population, right? So maybe use another train set, then I will get something like this, and I don't know, maybe something like this, and we know that even though on average we're hitting at a target, we're capturing the pattern, but the variance is large. So this is called overfitting. So that was a representation of overfitting in regression, and here is a representation of overfitting in classification, right? So this is classification example, and how do we know that? Because look at that, we have x1, let's say, and x2, and these shapes, cross versus circle, is basically our y level, right? So our target variable is categorical. In this case, two classes, a cross, green cross, and let's say these are brownish circles, right? Now again, and these red lines are our classifiers. So the red lines that we see are classifiers. We're going to talk about different classification models and regression models down the road, but the visualization, it should be very straightforward to follow. Okay, so in the first case, the model is underfitting because, as you can see, it's a very super simple model, and it's underfitting. It means that the bias is going to be large because on average it's not classifying the data properly, right? And on the very far right, we are overfitting. So this is an example of overfitting classifier. So even though the boundaries, the classifiers are doing a perfect job in this data set, if I use another representation of the data, this is going to be performing very badly, right? Because this complexity is going to comes at a cost for us, right? It's not going to be helpful down the road. It's a complex model, is overfitting the data, and it's not going to be generalizable to a new data, right? So let's summarize all these things in bullet points. So the model fits the training data too well when you're talking about the concepts of overfitting. And it's not predicting well in the new data, right? Not surprisingly. We also say that the model fits the noise in the training data. Find a pattern that does not exist. So for example, in this example, or in this one, maybe this is not the pattern. The pattern is something as simple as this. And the model is, that complex model is capturing something which does not exist. It's basically capturing the noise instead of the pattern in the data. Okay. And we also say that the algorithm is memorizing or has memorized the data rather than learning it, right? So when the model is complex, when the model is overfitting, we say that, okay, it seems that the model is just memorizing, the machine is memorizing the data instead of learning from it. It means that it cannot be generalizable to a new data set. Or simply we say that the model is too complex. I think we already looked at this concept multiple times so far. All right. Let's talk about how we can mitigate overfitting, right? So the main techniques used to mitigate overfitting risk in machine learning models are basically two things. The first one is what we call complexity reduction or regularization in general. Okay. The idea behind complexity reduction is that, so if you focus on this chart, we say that, okay, we want to reduce the complexity of the model, and hopefully by doing that, yes, we're going to increase the bias a little bit, but it's going to help us to reduce the variance a lot, right? And a combination of the two is going to be reduction in the mean squared error in general. So, right, this is what we call complexity reduction or regularization. Down the road, we're going to see examples of these things in the future lecture videos. Another approach is what we call cross-validation. Basically, we're going to estimate the test set error by a technique called cross-validation. And the advantages of that is that by doing cross-validation, we can calculate the performance metrics in the cross-validated data and see where the performance metrics is smallest, right? So if it is classification, we can look at accuracy. If it is regression, we can look at our RMSE. When the RMSE is minimized, and we know that that's the cross-validated RMSE is minimized, we know that it's an estimate of the test set error. So basically, we are visualizing this thing, and we're going to pick the optimal level of complexity where the performance metric in the cross-validated data is minimized. So don't worry about these two things. We're going to talk about them in a future video, but this is just a general concept of the two. Okay. Okay, so let's conclude this episode by going over the question of the day. Okay, so this is a question. I want you to think about it and write down your answers in the comment section. What kind of machine learning concepts this picture is referring to? It's a funny one, right? So what do you think? All right, and so until the next episode, take care. See you in the next one.